So in this video, we'll be discussing about some of the important relations in quantum mechanics, but we won't be discussing them in details, but briefly mention the important principles that is useful in terms of semiconductor theory. First, we will see what is Planck's relationship. With respect to semiconductor theory, the important point to note here is that the energy E associated with a photon is equal to h nu, where nu is the frequency, okay, and h is the Planck's constant. And the value of Planck's constant, it's good to know that it is a really small number, that is 6.62 into 10 power minus 34 joule seconds. Okay, now you might be familiar with the relationship between frequency and wavelength, that is c is equal to nu lambda, okay, where c is the velocity of light in vacuum, that is 3 into 10 power 8 meter per second, and lambda is the wavelength. So by substituting it, we can write E is equal to h nu or hc by lambda. From here we can calculate nu as c by lambda. Substituting here, we'll get hc by lambda. So one more point I would like to mention along with this, that is the Bohr's frequency condition. Suppose we have an energy level, let's say E1, and we have another energy level, let's say E2. There is an electronic transition from E1 to E2. Okay, so the energy that is released could be released as a photon, and the wavelength associated with that photon is given by Bohr's frequency condition, which is a direct consequence of Planck's relationship or Planck's-Einstein's relationship. So what it says is that, let's say this energy difference, that is E1 minus E2, let's say delta E equal to E1 minus E2. That is simply the energy difference between these two energy levels. So what we have said so far, we have an energy level E1, another energy level E2, and there is an electronic transition from E1 to E2, and we have taken that energy level difference or the energy difference as delta E. So the relation is delta E is equal to h nu. It is nothing new but the direct consequence of Einstein-Planck's relationship. We will discuss about wave-particle duality. Some properties of light could be explained when considering it as a particle, and some others could be explained when we consider light as a wave. It was found that similar to light, even particles like electrons have wave nature as well as its own particle nature. So all we need to know that electrons has both wave nature and particle nature. Just now we have seen that electrons have wave nature as well as particle nature. Now de Broglie's relationship relates the wavelength of an electron with its momentum p. This is an important relationship, that is lambda equal to h by p, where p is the momentum, h is the Planck's constant. So Heisenberg's uncertainty principle state that the more precisely we are looking for the position of some particle, so we can deduce its momentum with lesser precision. So if we, let's say, so x be the location and p be the momentum, okay, so the more precisely we are looking for the position of some particle, less precisely we can find out its momentum. So he gave this relationship, that is delta x into delta p is always greater than or equal to h by 2. So its value is h by 2 pi, where h is the Planck's constant. Now what is delta x and delta p? They are the standard deviations in measuring position as well as momentum. Sometime back we have learned that h, the value of h is really small, that is 6.62 into 10 power minus 34 joule seconds. So this is a really small number. So this uncertainty may not be visible when we are dealing with large objects, but when it comes to electronic level, this effect gets more visible. So we'll now discuss Pauli's exclusion principle. I have missed it earlier. Now it simply says that in an interacting system, no two electrons will have same quantum state, or no two electrons will have all the properties similar. Okay, so it says that it is impossible for two electrons of a Pauli electron atom, that means there is some interaction between these electrons, to have the same quantum state. So we haven't discussed about this relationship in much detail, but we have seen a summary. We have seen that the Planck's relationship, that is E is equal to h nu, and we have seen that electrons have particle nature as well as wave nature. So wave nature as well as particle nature. Then we have seen de Broglie's relationship, that is lambda equal to h by p, which relates the wavelength to the momentum of the particle. And we have seen that there will always be some error when we try to precisely determine the position. We may get way off results with its momentum, and this will always be greater than this value. And we have seen that right now that Pauli's exclusion principle, which states that it is impossible for two electrons of a polyelectron atom to have same quantum state. So this is just an outlook of some of the important principles in quantum mechanics, but you must remember these relationships